Right, hello everyone. So this is the fourth part of the periodicity topic, and you'll be pleased to know it's the final one. So where have we got to so far? So part one, we discussed the general structure of the periodic table, metals, non-metals, groups, periods, and all that kind of business. Then we looked at the effect of melting point and boiling point as we went across the period, and we related that to the structure of bonding. We've got these on the next slide as well. Then we looked at the atomic radius, and today what we're going to do is look at the first ionization energy, the effects there. So there's a little bit of a quick recap. We looked at melting points and boiling points. We divided it into sort of three sections. So we've got the metals, and they increased between the sodium, magnesium, aluminium, because we increased the charge on the center. It's metallic bonding, so it's the Na plus, Mg2 plus, Al3 plus centers in there, so it's a stronger electrostatic force or attraction. Silicon was macromolecular, so it was a giant covalent structure, so there were many covalent bonds to break in there. And then we had simple molecular substances down here, so we had weak intermolecular forces, like van der Waals. And then argon over here was the lowest, so it just exists as atoms, so the interaction between those argon atoms are even smaller, so therefore a lower melting point and boiling point. Right, then we looked at atomic radii, and we could see that they decreased as we went across a period, and this was all about the increase in nuclear charge, pulling those outer electrons closer to the nucleus as we went across. Right, so what we're going to look at today is first ionization energy, and just as a kind of a recap, so what was first ionization energy? Well, it's the energy required to remove 1 mole of electrons from 1 mole of gaseous state atoms. So we're just removing 1 electron from each of these atoms. And what we're going to look at is the trend across period 3. Okay, so I'll just put this up there. We'll describe this in more detail in a minute. Okay. First thing I want to do is just go back and look at what happens as we go down groups or between periods, because that's what we're doing. So period 2 over here, we've got lithium, then period 3 sodium, so this is the period that we're interested in. And as we go down the groups, we can see that the first ionization energy decreases. It becomes easier to remove with the outer electron. So this comes down to atomic size, so it's the distance from the nucleus. So it's this electron here we're removing in lithium, so only in the second energy level, then the third, fourth, and so on. So the further it is away, the easier it is to remove. So even though the nuclear charge is greater, all these inner electrons are going to be shielding this outer electron. So I should have included those there. Okay, so they're all going to be shielding the outer electron. So it's easier to remove the outer one. Okay, so describing trends across the period. Okay, so just for reference, I've got the element symbol, electron arrangement, and then the first ionization energy. And I've taken these, and what I've done is I've just plotted these in a graph. Okay, so there's my graph. So we can see straight away that the general trend is it increases. So the general trend increases. Okay, so that's one thing, and we'll explain these in a minute. And the second thing is we can see there's a couple of points where it doesn't quite fit the trend. So it's this change between magnesium and aluminium, and this point over here between phosphorus and sulfur, where sulfur is a little bit lower than perhaps we would expect. So the general trend is going to increase. However, there are two deviations from that, which you've got to be able to explain, which is what we'll do on the next slide. Okay, so exactly the same as the last one, to be honest. It was just so I didn't have to delete all my annotations. Okay, so now we're going to explain them. And we're going to make reference up here to the electron arrangement. So, get my pen back. Right, so our general trend is increasing because we're increasing the nuclear charge, much like the atomic radii explanation, without real significant changes to the shielding. So those outer electrons are being held more tightly. They're being pulled in closer and held tightly, be it by the increasing nuclear charge, the number of protons in the nucleus. Okay, so that's the explanation for the general trend. Now, for these deviations, what we're going to look at between magnesium and aluminium. So, aluminium now has got a p electron, whereas magnesium has only got s electrons in there. So, what this means is, in our atom, so we've got our, I've got my nucleus, and then I've got an s orbital. Okay, so that represents my s orbital. We then have a p orbital as well, so I'm going to show that as a green sort of dumbbell shape sort of thing. Okay, so there are regions in these where the s orbital, well, the electrons in there are going to be shielding slightly the p orbital, and also the p orbital is slightly further away. Okay, so it's slightly further from the nucleus, and the electrons that are in there are going to be shielded by the s electrons. So because it's further away, slightly more shielding, therefore this p electron here is more easily removed. So it's going to have a lower ionization energy. So phosphorus and sulfur. Okay, so drawing our attention over here. So what's going on here? Well, I'm filling up the p orbital for both of these. So why is it a difference? So if we look at the phosphorus, I'm going to show it as the my little boxes. Okay, so phosphorus has got 3 electrons filling those 3 p orbitals. So if you remember Hunt's rule, where they fill the separate ones, so I call it the seats on the bus rule. So they're always going to sit on their own unless they have to double up. Okay, you're always going to choose that empty seat on the bus rather than risk having to sit next to that smelly tramp. So each electron in the p orbitals of phosphorus is sitting in different sub-p orbitals. Now for sulfur, we're going to have to double up for one of these. So this one has got 2 electrons in one of the p orbitals. Because of that, what we're going to have is a little bit of electron repulsion. So that repulsion there is going to make it a little bit easier to lose that second electron. So it's a bit more likely it's going to get off at an early stop. Okay, it's sat next to that smelly tramp. So that is the reason why sulfur is slightly lower in ionization energy than the phosphorus. Now, very quickly, if you were asked to sketch these graphs, what they would look for is you showing them increasing, and you make sure that this one, this point for aluminium, is between these. Okay, the actual position you don't need to know that it is 590 kilojoules per mole or whatever it is. I don't know what it is, but you need to show it between these 2 points here. So somewhere between those 2. This one needs to be higher than this one. And then it's a similar story for this one. Even though these are quite close, I would show this a little bit more obviously down here if you were having to sketch this. So again, between the value got for silicon and the value for phosphorus, and again, chlorine has got to be higher up than both of the phosphorus and sulfur. Okay, hope that makes sense. If not, send me a question. More than welcome. Okay, next one. Okay, so our general trend. So the first ionization increases across the period, and this is because of increase in nuclear charge and no significant change in shielding. Then we've got to explain our two deviations. So between magnesium and aluminium and phosphorus and sulfur. So aluminium is lower in IE than magnesium. And this is because the outer electron, the most recently filled, so the one that's going to be removed first, is in a p orbital, a 3p orbital, which is slightly further from the nucleus, and it's going to be slightly shielded by the s electrons in there. Then our deviation between phosphorus and sulfur, and this is when we're doubly occupying our p orbitals. Okay, and don't be afraid of drawing your little boxes out to explain it. Help get that message across. And it's all about the repulsion that you're going to get in there. So over here you're talking about distance and shielding, and then for phosphorus and sulfur you're going to be wanting to talk about the repulsion. Okay, so what have we done? We've described the trend of the first ionization energy across period 3, and we've looked at the deviations between magnesium, aluminium, phosphorus and sulfur. We've explained this trend in terms of the nuclear charge and where those electrons live in, and this also helps serve as evidence for the existence of orbitals. It helps back up what we know. So this experimental data we get for the first ionization energy backs up that theory of sp and d orbitals and all that kind of nonsense. And then we also explained the difference between the periods as we went down the groups. Okay, hope that's all alright. Any questions, let me know. Yeah, and good luck.